we have our next speaker coming up. We're going to continue our Tuskegee University research series from yesterday. We have Seyyed Salehian, who's an assistant professor, who will be speaking, and Jair Harris from TSU will be introducing him.
All right, thank you very much. I really appreciate it. All right, and again, thank you so much for the previous speaker. I have really loved to hear the fact that I really love to hear the fact that our NSBE chapter is improving. But my name is Jai Alexander Harris. I am a senior at Texas University. I'm also the vice president of NSBE of my chapter. I'm here to introduce the infamous Dr. Dr. Seyyed Saman Salehian. Dr. Salehian is serving as a tenured track assistant professor at the Aerospace Engineering Department of Tuskegee University, Alabama. Since January 2021, he obtained his PhD in aerospace engineering from Embry-Riddle Aeronautical University, well, ERAU for those of y'all. In August 2020, he had previously obtained his master's degree in aerospace engineering from ERAU with distinct in May 2016. His research areas of interest include computational aerodynamics, aeronautics, and multi-phase flows. He has authored and co-authored various journal publications and conference papers in the International Journal of Aeronautics, Applied Science, and AIAA. He is currently involved in research activities funded by NASA and the Departments of Defense, conducted at Texas and at Tuskegee University. Ladies and gentlemen, it's my honor to present to you Dr. Salehian. Dr. Salehian, take it away from here.
Okay, well, hello everyone, and welcome to my presentation. Sorry about the delay. I was running into some technical difficulty, and I'll try to make time for that. My name is Sam Salehian. I'm an aerospace engineering major myself, and I'm an assistant professor at Tuskegee University at Aerospace Engineering Department. I graduated from Embry-Riddle Aeronautical University in 2020 and joined Tuskegee University in 2021. I hope you all saw the introduction. My work today is going to be about a vortex dominated that flows over delta wings and how we use numerical simulations and experimental measurements to deal with this phenomenon using the thrust vectoring. So today I'll talk about the background and motivation, the experimental setup that we have at Tuskegee University Aerospace Engineering Department. I'll talk about the numerical approach and some of the results and the concluding remarks and the future work. So why is it even important to study delta wings? So the delta wings are used in a variety of aerospace vehicles. The most important and the most famous one that we all know and are familiar with is the highly swept wings of highly maneuverable fighter aircrafts. But I also have on the bottom the pictures of each of these bullet points of future supersonic civil transport aircrafts, current and future unmanned combat air vehicles, mini and micro MAVs. A lot of them have more or less a delta wing platform, as well as gliders. And in a lot of these cases, we care about the safety of these vehicles. We want them to remain in air and have a safe and safe flight without any disruptions. So it is important for us to understand the aerodynamics of delta wings. So many investigations have been carried out over the years for delta wings, and we typically look at slender delta wings and non-slender delta wings. To just summarize the aerodynamics of these many years of research, basically, if you look into delta wings, if you start looking into your basics aerodynamics, there are what we call leading edge vortices. These are the roll-ups of airs coming trying to escape the high pressure under the wing to the top of the wing, over the wing. And this creates a counter-rotating, let me see if I can show my pointer here, these counter-rotating vortices here. And these vortices basically are the reason that these delta wings are highly preferable in high angles of attack, because they produce a lot of lift. But there is a phenomena that's called vortex breakdown at certain angle of attack, especially at high angles of attack. This starts to break down and causes vibrations, flow unsteadiness, loss of lift, and loss of flight control, and basically, there's something that we do not want in our aerospace vehicles. So we are going to talk about that a little bit, and also the trailing edge vectoring jets, and many of the fighter aircrafts have already implemented that technology by having jets that are vectored, basically coming at an angle, and that causes some performance improvements. So the experimental setup that we have a water tunnel at the Aerospace Science Engineering Department at Tuskegee University. This is basically right here is the CAD model of our water tunnel at the Aerospace Engineering Department. And here's the actual picture of a delta wing with attached pumps that will provide the thrust vectoring. Then you can see we have our delta wings in a simplified aerodynamic shape, because we are interested in the fundamentals of this. Now, we don't model the full aircraft with all the details. We're just eliminating the aerodynamics of delta wing itself and the jets. So the way that we use experimental setups, we have a test model in here, and we have the water tunnel running, and we have very high resolution 3 PIVs, particle image velocimetry, that collect data on every point of the grid that we provide here. Also, we use numerical approach that basically we look at the delta wing, the shape of the delta wing, which has certain chord and certain. We use the here we are looking at the 80-degree sweep angle. We use a flat plate. Basically, we consider, as I mentioned, the fundamental aerodynamic shape, and we look into 20-degree vector jets that provide 5 times the jet ratio. And we provided that through a kind of a literature review to look into what is the jet velocity of typical fighter aircraft that perform high angles of attack maneuvers and have jet angles. And these are basically the numbers that we compiled together. So the first setup, I'm going to look at the basically the numerical approach. The numerical approach that we use is a transient incompressible turbulent flow solver and open foam, which is a fine volume approach. And we use the second order temporal and spatial discretization. And with the method that we use to capture turbulence is called the detached eddy simulation, which is a hybrid LES and RANS. And if need be, I'll start talking about the details of this in the Q&A. The computational grid is a high fidelity hex-dominated unstructured grids. To capture the boundary layer, we use very low grid spacing near the flat plate. And here I have certain just figures of merit to show the scale of the fine solution that we have is a grid of 13 million cells. And we use some refinements near the jet to capture the velocity and turbulence of those vector jets. So here we can see that we definitely need high resolution to capture all this turbulence and all this unsteadiness that happens over the wing. We're looking at the baseline case, no jets, and we're looking at the variable called Q criterion. Q criterion is basically a variable that is derived from vorticity, and it need be, I can talk about the details of the calculation, but basically we're looking at the rotation of air particles, and that's a property called vorticity, and we are looking at the non-dimensionalized one. So if we use a coarse grid, which is the low resolution, we don't capture those fine fluctuations or fine unsteadiness, but we still get that main vortex and counter-rotating vortices. So to be able to capture these, we will compare our coarse grid with fine grids cross sections at different cross sections of the wing. We're looking at 25%, 50%, and 75% that we can see. If I use the fine grid, not only I can get the extent of these compared to my PIV, but also get very good resolution inside the vortex core. And to basically get a better comparison with this, we look at these cross sections at 50% and 75% of the chord, and look at these two rings as center line of those two rings. If I cut a cross plane and those counter-rotating vortices, I will see these two circles that, and I can, here we're looking at the line that goes through the center line of that. So if I look at the PIV, you can see that our experimental numerical results actually predict the location, the peaks, as well as mostly for the near the trailing edge, the extent of it. We have some discrepancy here, and this discrepancy is mostly because in our PIV grid is very coarser or not as refined as our numerical simulation. So we use PIV mostly to get the general characteristics, but we use CFD where we can look into more details, finer structures inside those vortex cores. So then we started looking at what happens if I look at high angles of attack. So first, before we going into higher angles of attack, we looked at an aircraft that flies at 30 degrees of angle of attack, which reasonably compared to typical aerospace vehicles is still high. We don't see any vortex breakdown. It only happens when you look into 45 degrees on angle of attack, since the vortex breakdown happens. And even if you go higher, that becomes severe, and you can see the fluctuations increase, and then basically you lose the lift generating mechanisms on the surface of your aircraft, and basically you lose aircraft control, eventually aircraft lift, increase unsteadiness, increase fluctuations, and basically this is what we don't want when we put things into perspective in terms of air safety. Then we started looking into these, comparing at high angles of attack. As you can see, right around 50%, we can see even at 75%, the 30-degree angle of the vortex remains attached. You have those vortex cores, but right here you don't see any cores. Those are gone. It's all dominated by these wake of the flow, and that's even worse for the 60 degrees, which happens even near the leading edge. So to be able to visualize this better, we are looking at the cross section. So if I take the 30-degree angle of attack and put the cross section at the center line, and we also calculate that center line and compare it with the experiment that center of that vortex core happens at 86 degrees, more or less. That gives me the 30-degree case, shows me a very attached type of flow that is a vortex core that remains connected to the surface. But if you go to 45 degrees, this is very simply what the vortex breakdown happens, and we are estimating that to start at somewhere around here, mid-core. And very high angle of attack 60, this is already vortex is broken down here, very closer to the leading edge. So now we start looking at the vectoring jets. So I'm comparing, because 45-degree angle of attack was a special interest to us, we are focusing on this one because this one has an attached vortex and then breaks down. So if I look at the jet off versus jet on, here you can see the vortex, the turbulence or the vorticity induced by the jets that is affecting this flow very, very effectively. To see that effect specifically, we wanted to compare our experimental results with CFD results. So here on the left, we have the jet off case, which basically compares cross-section by cross-section of the surface of the delta wing. Top is, of course, our numerical simulations without the jets on the left, and the right-hand side is the numerical simulation with the jet. On the bottom, we are looking at the flow visualization, which is a dye visualization, and we can look at that vortex breakdown that's happening for around 40%, as I had shown for the 45-degree angle of attack, both numerical and experimental cases. And that is by injection of those jets, that is brought even further downstream. This may not seem a lot and going from 40 to 45, but in terms of the level of lift generation and also the lift loss due to these vorticities, that can cause a lot of problem. If this happens near the leading edge, you lose lift and increases a lot of fluctuations. But for us, this part, at least at this part of the research, it was important to see if this jets, if are injected with the right velocity, minimum enough to change this, is this effective? We saw it is effective. So just some concluding remarks, because I was running late. I'm trying to go over these faster to leave some room for Q&A, because numerical results show that we have here that we adopted a detached simulation can predict the location and development of leading edge vorticities. And we also conducted a grid sensitivity to see how accurately our numerical models can be used to be compared with our experimental PIV. And we did look at some of the higher angles of attack to see the 45 degrees for the 80-20, 80 degree sweep angle, 20 degrees jet is of specific interest for us. So we isolated that and started looking at the vectoring jets. And basically we saw that those vortex structures indicated a positive Q criteria, basically, and the location of that, as we saw, was pushed backwards or near the trailing edge, and basically it is a positive sign, or shows the effectiveness of trailing edges. So I want to acknowledge the support of the Department of Defense for this research, and also the high performance computing resources from ASC for providing the computational resources for us to run the numerical simulations, and of course the DoD grant that made this research possible. Also, I would like to thank my colleagues at Tuskegee University, Dr. Khan and Dr. Aji, both professors and department heads, one at Aerospace Engineering Department and the Dr. Aji at Department of Mathematics, who both provided their knowledge and technical support for this research. And also, I want to thank two of our graduate students at Aerospace Engineering Department of Tuskegee University, Hakeem and Anton, which made the PIV measurements that are very complex and tedious work sometimes possible. And most importantly, thank to all of you for listening to my presentation, and